Hey everybody, happy Tuesday to you. Today we're going to do something similar to yesterday. Like I mentioned yesterday, we're going to slowly build and add more and more to the things that we're doing to these trig graphs. So if you are keeping up with everything, and hopefully most of you are, I know that most of you are, you know what the sine curve looks like, you know what the cosine curves looks like. So yesterday we changed the amplitude by putting a coefficient in front of the graph or the equation, and that stretched the graph out vertically. Today we're going to see what happens when the period is affected. So first we get to talk about what that means. The period of a periodic graph, called periodic because of that reason, is the distance, the horizontal distance before the function repeats. Basically, if I was able to slide this over, how far would it slide before it landed right on top of itself? What is that smallest distance? And so the one that I'm looking at right now looks like, let's see, I'm gonna try to find, well, I guess that point right there, right at the origin, where this could be a sine graph that is starting at the origin, going through one full complete cycle. By the time it gets to about, looks like about 9. It looks like the period of this graph is about 9. Just like the amplitude, the period is always positive. Probably not going to emphasize that quite as much as I did yesterday, mostly because people tend not to do that with the period, even though sometimes they do with the amplitude. So just a quick look. These are the same graphs that we had yesterday, and I'd like to take a look just quickly at what the period of these graphs would be. Looks like the first one goes through one full cycle. By the time it makes it to 2, it looks pretty solid 2 for the period of that graph. And I chose to go from the origin, but really we could go from any point to any other corresponding point. I could go from the peak over here to the next peak that shows up. So from negative 1.5 to 0.5, but that's still a distance of 2. Or we could go from the very bottom. How far is it from negative 0.5 to 1.5? We'll get the same thing no matter how we do that. For this graph, I can't really start at 0 because I don't get to see one full cycle. So I'm going to go back here and look at this point. Go through one full cycle. By the time it gets there, looks like it's a distance that's a little bit bigger than 6. And if this was not an honors class, I would probably just take a guess and say it looks like it's about 6.25 or something like that. But this is an honors level class. And so I'm going to talk about how it's not a coincidence that it looks like the horizontal distance, the period, well, this half of it is a little bit bigger than 3. This half of it is a little bit bigger than 3. Not a coincidence that it's probably around pi. And when we're dealing with the period of graphs, especially when we're dealing with radians, we know that the period of a regular sine or cosine graph is 2 pi. So for this one to be stretched out and have a period that is, well, I guess it's still 2 pi. But if you said 6.25, I can't take points away that even could be the answer. I don't know. Actually, I do know. I made this graph, and it is 2 pi. But it's hard to tell from the graph that it's exactly 2 pi. And the next one has been shifted up vertically. So as I'm looking at points to compare, I could look at these 2 points here down at the bottom. I could look up at the top. I'm going to look at this point right here because it looks like it's crossing. It looks like the midline halfway between 0 and 6 is right about there. And so by the time it makes it through one cycle, and here we are again, it looks like it's that same little bit bigger than 3. And if you said 3.1 or 3.2 or 3.15 or 3.14159 or something like that, that'd be fine. But the actual period of that graph is pi, and we could get that by measuring this distance or this distance, but of course it's easier to measure starting at 0. And then finally the last one that I've got here, looks like a smaller period on this one from here to there. Looks like it's about 1 point something. And again, you could take a guess. If this was not an honors class, I would probably just write down about, I don't know, 1.4 or something like that, or 1.5. But because this is an honors class, I'd like to talk about a strategy to get a better number out of this. I am going to look at, um, let's see, I'm trying to find a good place to start this one. I think I'm going to start it right here and look at how far it goes from this point, not just one period. So one period would be this distance, which again, it's 1 point, now it looks like maybe more like 1.6. But if I go all the way to the end of the next period, I see that we're right back at that usual, it looks like it's probably about pi. And so if 2 periods is 1 pi, then 1 period is probably right about half of a pi. I'm going to go with pi over 2 as the period. But again, if you said 1.6, you're not wrong. It's hard to tell from a graph exactly what it is. I'm just mostly making sure that we're okay with looking at a graph and figuring out what the period is. And so we got to figure out um, how the equation affects the graph, just like we did yesterday. We know what sine of x looks like. We know that it's got a period of 2 pi or 360 degrees. And so what happens when I put a 2x, sine of 2x, or sine of 5x, or sine of 10x, or sine of a half of x? What's going to happen to the graph? So just like we did yesterday, I'm going to go to Desmos. All right, here we are in Desmos. And I found out yesterday with the video, I apologize. I didn't know it when I was making it, but I found out later when I was watching it that you guys couldn't see what was happening over here on the left side. I've changed the shape of my window. Hopefully this is working better, but I won't know until after I look at the video. So hopefully this is working. We need to take a look at what happens when the value of the number that's multiplied by the x changes. So right now I've got k equals 1, and we can see I've got a sine graph. It goes through one full cycle. By the time I get to 2 pi, hopefully you can see that on this graph. My scale, I made it in multiples of pi over 2 so that we'd be able to see exactly what the period is as I change this. So I'm going to start by making the k value larger. I'm going to make it 2. Take a look at what happens. Now the period of this graph looks like it makes it through one full cycle by the time I get to pi. So it went from 2 pi to 1 pi when I changed the value of k from 1 to 2. If I double it again and go all the way up to 4, we see that now this graph has a period of pi over 2, half of what it was. So doubling the k value cuts the period in half. Or if I go in the opposite direction, if I go from a period of 1 to a period of 1/2, oh, it's not going to let me do that. Oh, there it is. And so now the period is 5. I'll have to zoom out to see what this is. Now it goes through one full period by the time I get to 4 pi. And the same is going to be true for a cosine curve. I'll switch this around. We'll take a look at a cosine graph from the beginning to one time through the period. It takes 4 pi, which is twice as much as what it was. And so making the k value larger makes the period smaller. Making the k value smaller makes the period larger. And if I flip over to negative values, it's the same idea. We tend not to see this as much, but we see that it is taking the graph, and well, I guess it's hard to see with cosine because it's actually flipping over the y-axis. But we don't really see that with cosine because it's symmetric to the y-axis. So I'm going to switch this back to a sine graph so we can see this a little more easily. So here we see when k is a positive value, the graph is increasing as we pass through 0. But if I make the k value negative, now the graph is decreasing. It's been flipped over the x-axis. So to figure out what the period is based on the k value, I'm going to put it back to 2 and say that we were starting at a value of 2 pi. The k value is 2, which means our period is half of 2 pi. We're taking 2 pi divided by 2. If I go all the way up to 10, if the k value is 10, we're going to find the period of this graph by taking 2 pi, the original period, and dividing by 10. 2 pi divided by 10 is 0.2 pi, which I suppose is about 0.628, and I'm not sure. Well, I guess it's just going to show us in terms of pi. the place where it crosses there, 2 pi over 10, which is the same as pi over 5, and that is the period of this graph. So there's our general rule to take the equation and figure out what the period is. Take 2 pi divided by the k value, and that tells you what the period is. There will be a slide in just a moment that lays that out for you. All right, back to the notes. And so I want to take a look, since we didn't get to see degrees very much with Desmos. Desmos, I guess, uses radians. There's probably a setting for it, but we would find this information if I did a whole bunch of equations using Desmos. Y equals sine of x. If we're doing degrees, then of course the period is 360 degrees once around the circle. And we'll see the same idea. As the number in front of the x gets bigger, the period gets smaller. And it's not just a random smallness, it's very specific. We would take, I'll put the rule up in just a moment, but we'll take 360, what our starting value is, and just divide by whatever the number is in front. If I've got cosine of 90x, 360 divided by 90 gives us 4 degrees. And so that's the period of that graph. If I have fractions, something like sine of pi over 2, I suppose we can think of this as 1/2 times x. And so I would do 360 divided by 1/2. Dividing by 1/2 is the same as multiplying by 2. So this graph would have a period of 720 degrees. For fractions like 2/3, we can think of this as 2/3 x. Our period is going to be found by taking 360 divided by 2/3, which is the same as multiplying by 3/2. So 360 degrees times 3/2 gives us a period of 540 degrees. So the shortcut depends if we're dealing with radians or degrees. Whatever the number is that is in front of the x, the coefficient on the x, we find the period in degrees by taking our usual period, 360 degrees, and divide by that value, 360 divided by k. And if we're dealing with something in radians, we take 2 pi divided by k. That's scaling it either up or down, depending on if k is smaller or larger than 1. And so we'll usually see equations in this form. If you're a little bit uncomfortable with fractions in this form, you can take out the number and say that x over 2, half of x, is the same as 1/2 times x. That gives you a number that you can then plug into a calculator, divide by 1/2 to figure out what the period is, or if you want to convert that over to a decimal, that's okay too. But some numbers are a little bit less convenient than 1/2 is for converting over to decimals. At this point, we need to take a quick crash course on fractions. I realize that many of you have probably been dependent on calculators, and dealing with fractions is something that you're maybe not 100% on, but I want to take a look at some specific skills, because this will be important when we're making graphs and figuring out what periods are. First one, half of 4/3. Well, of course, half of 4/3 is 2/3. If I make the numerator half, then the fraction becomes half as big. 2/3 is half of 4/3. And related to that, half of 4 pi over 3 is 2 pi over 3, which will come in handy when we're making graphs. If I have a 1 in the numerator or an odd number and I want to divide this fraction in half, I'm not going to call it 0.5 over 3. I'm not going to mix decimals and fractions. So instead of saying a half over 3, I'll say that half of 1/3 is 1/6. If I double the denominator, the value of the fraction is cut in half. And then counting by sixths, and this comes in handy when we're making the scale on our graphs. Counting by 6, we'd have 1/6, and then 2/6, 3/6, 4/6, 5/6, 6/6, et cetera, et cetera, et cetera. And these fractions is be counting, but then of course we can simplify. 2/6 is the same as 1/3. 3/6 is the same as 1/2. 4/6 is the same as 2/3. 5/6 is 5/6. That's a tough word for me to say right now. And then 6/6 is 1. Nothing too crazy there. So let's take a look at a few problems. Your homework questions are going to look like this. Oh, I wanted to have something there. Let's do, for this first one, let's do sine of, Oh, I don't want to. Well, if I accidentally do one that's on your homework, I guess that's not the worst thing in the world. Let's do sine of 6x. Y equals sine of 6x. And let's do this one in degrees. Since my k value is 6, I'll find my period by doing 360 degrees divided by 6 divided by the k value. That gives me a period of 60 degrees. So it's going to go through one full cycle by the time we get to 60 degrees. Yesterday we didn't have to worry about the period. Today we don't have to worry about the amplitude. The amplitude of this graph is just 1. If I had a number in front, that would change it, but I don't. And so now, as we make this graph, yesterday we had to adjust the vertical. Today we're not going to. It's going to go from -1 to 1 all day today. Come back later this week. We'll see what happens when we're dealing with the amplitude and the period. But this one's just going to go from -1 to 1. It's going to have a period of 60 degrees. And so as I am making my graph, I'm going to advise that you think of this in 4 chunks. I'm going to go 1, 2, 3, 4 chunks. At the end of that last one, I'll call that 60 degrees. Actually, I take it back. I don't know if I want to deal with this in 4 chunks. Well, I do want to deal with it in 4 chunks, but I think I'm going to change how far I'm spreading these out. Sorry about this. I'm changing my mind on the fly. I'm actually going to spread them out by a little bit more. I'm going to have 3 of these representing these intervals. I'm going to put 60 degrees at the end of the 4th interval. Now, the reason I do that is because this is the full period, and this gives me, well, the one that's halfway there, that's half of a period. 30 degrees is half of the full period. Whoops. 30 degrees. And then half of 30 degrees, 15 degrees. And so now, as I'm counting off, if this is 15 degrees, then each of these intervals is 15. So 15, then 30, that means this one must be 3 times 15, or 45. The next one, of course, is 60 degrees, and then after that would be 75 degrees. All right, so now, as I am making my graph, this is a sine graph, so I know that it's going to start at 0. And it's increasing because it's a positive sine graph, so it'll make it up to +1, back down to 0, down to -1, up to 0, and then I'll go a little bit past that. We'll go out to 75 degrees. And the reason I wanted to divide it up like this into intervals of 3, I want to think about um, if I look at this interval, the first fourth of the period, I'm going to think of this almost as if it was back to 0 to 90, where if this is 0 and 30, 60, 90, I know what sine of 60 degrees is. That's 1/2, and that's one of those numbers that's an easy number for me to keep track of. Sine of 60 degrees would be square root of 3 over 2, and that's a little bit tougher to see where that goes on this graph. I think it's going to be up here a little bit, but I'm actually only going to label this one because 1/2, I know what 1/2 looks like. Likewise, when I'm a little bit, this would be the scaled down equivalent of 150 degrees. Sine of 150 degrees, there would be another positive 1/2. So this scale has been shrunk down by a factor of 6, but that 1/2 is still going to be there. And so if I look at the places where it crosses the axis, if I make my horizontal scale go by these intervals of 3s, that means the first one is going to be 1/2. The third one is up at the top. The fifth one is down to 1/2. And of course, we're at 0 and then -1/2. This would be -√3 over 2, but again, I'm not exactly sure where that is. This one would be -1/2. This one would be +1/2. And this is going to help me make a little bit more accurate graph than what I was doing yesterday. We'll see what this looks like. And so far, I'm already much happier with this graph than the one that I was making for you guys yesterday. I'm even missing my dots by a little bit, but there we go. That's a pretty good graph of y equals sine of 6x. The period of the graph is 60. No matter what you do for your horizontal scale and your vertical scale too, make sure that I can see at least one full period of the graph. All right, let's try one that goes in the opposite direction. I'd actually like to do cosine of, let's go for, how about 2x over 5? We'll see what that looks like. Amplitude is 1. I'm going from -1 to +1. That's not something that I'm worried about today. But then to find my period, let's see. Let's do one more in degrees, and then we'll switch over to radians for the next one. The period is going to be 360 degrees divided by, and here's that k value of 2/5. This is 2/5 x. So to find this, I'm going to divide by 2/5, but that's a fraction inside of a fraction. So instead of instead of dividing by 2/5, I'll take that 360 degrees and multiply by 5/2. And so that's going to give me the period 360 times 5/2. Let's see, half of 360 is 180. 180, I think that's 900. I'm just going to plug that in a calculator and make sure that that is right. But I believe that that is 900. And yes, it is. So I'm going to do the same thing that I did on the previous problem. I'm going to count off 3 intervals to get to the first fourth, 3 more intervals, 3 more, 3 more. The end of my graph is over there. 4 intervals. I'm going to make that my full period of 900 degrees. And then I'll figure out half of 900 is 450. So the halfway point will be 450. Whoops, I did it again. And then half of that is 225. So each of my marked intervals is 225. So 225, 450, and then 225 more than 450 must be 675. And then 225 more than 900 would be 1,125 degrees, which I don't need to put that on there. I just need to have one full period, but why not? Here we have a cosine graph, and so because it's a positive cosine graph, it'll start off up at the top, similar to what we saw yesterday. It's going to cross here, but then a reminder, because I've counted off by these intervals of 3, I can put a point right there at 1/2 and -1/2, down to -1, up to -1/2, and then 0, and then +1/2, and then +1, +1/2, and 0, the same points. And I'm just adding these 1/2s to get myself a little bit more definition on my curve so I can make my graph nicer looking. I'm sure you're all appreciating the splendid beauty of my graphs today. And as I say that, this what looks a little bit lumpy, but there we go. One full cycle, at least one full cycle of the cosine graph looks like that. And then let's do a couple problems in radian mode. Let's see, I believe the next one I do, I actually have got that as 2 pi x. I'm going to do, let's see, let's go with, how about 3x over, I just did 5. Let's do over 10, see what that does. Amplitude is 1. We're going from -1 to +1. No problem there. For this one, I'm going to do, instead of degrees, radians, and so we'll do 2 pi divided by 3/10. I'm going to skip ahead and right away say instead of dividing by 3/10, let's multiply by 10/3. And look at that, our period is 2 pi times 10/3. 2 pi times 10 is 20 pi. We've got 20 pi over 3. Interesting. 20 pi over 3. So I'll do the same thing that I've been doing. I'm going to mark off on my graph, counting intervals of 3 grid lines. The end of my fourth one is my 20 pi over 3. So half of 20 pi over 3 would be 10 pi over 3. And half of that would be 5 pi over 3. And so my graph, the way that I've got it labeled, the way I'm laying things out, I'm counting by 5 pi's over 3. So 5 pi over 3, then 10 pi over 3, then 15 pi over 3. But of course, 15 pi over 3 reduces. 15 pi over 3, let's see, would be 5 pi over 1. And then we've got 20 pi over 3, and then 25 pi over 3 for my last one. And I have to say, making this one up off the top of my head, I was a little bit nervous that 3x over 10 was going to be gross, but this is actually turning out pretty nice. All right, we're back to a cosine curve. So it starts off up at the top. It's going to go all the way through one full cycle. By the time I get to 20 pi over 3, halfway in between, it's down at the bottom. Halfway in between the top and the bottom, it is at the midline. And then what we found earlier today is that on my graph, the ones that are close to these midlines are going to be the positive and negative 1/2s. And then we play our lame game of connect the dots. Hey, that's looking pretty good so far. Of course, jinxing myself to make it start to go wonky, but there we go. There is at least one full period of the cosine curve. This is what y equals cosine of 3x over 10 looks like. And then one last example like this for today, the one that I actually had ready to go, sine of 2 pi x. Amplitude is 1. We're going from -1 to 1. No big surprise there. And we're going to find the period by doing the same thing that we've been doing. Take the period. We're doing radians. So 2 pi divided by that number that's in front of the x. Hey, check that out. 2 pi divided by 2 pi. The period of this graph is 1. But I'm still going to do everything the same way. As I mark my intervals, I'll go with 4 intervals getting to that 1. And so half of that is 0.5, 1/2. Half of that, half of a half is a fourth. And so we're counting by fourths. 1/4, 2/4, 3/4. 4/4 is 1, and 5/4 for the last one. And now we have a sine curve which starts at 0. By the time I get to 1, it will be back to 0. And this graph will go through one full cycle. So the halfway point is also at 0. The sine graph, a positive sine graph, starts increasing. And so we've got a graph that looks like that. I'm going to add my halves on either side of the midline to give myself a graph that looks like that. And so finally, one last graph for you guys to watch. Boy, this video is going to be a little bit long. I apologize. Hopefully this has been useful. We've got one more little thing to talk about, and that is I want an equation, and this is actually maybe even more useful skill. I want an equation for a sine curve that has a period of 45 degrees. Now to do this, we've already said this. The period of a sine or a cosine graph is 360 divided by that k value. Or if I'm doing radians, the period is 2 pi divided by that k value. Well, if I do a little bit of algebra with this equation, multiply both sides by k and then divide both sides by p, we end up with this equation. And it's kind of convenient that the way we're going to find the period from the coefficient in the equation is the same as how we're going to find the coefficient if I know what the period is. 360 divided by the period gives me that number that shows up in the equation, or 2 pi divided by the period gives me the number that shows up in the equation. So if I want a period of 45 degrees, well, I'll just take 360 degrees divided by 45 degrees, and 360 divided by 45 degrees is 8. And so my equation, and I'm going to go ahead and cheat on this one and just say y equals sine of 8x. And there we go. The number that's in the equation is 8. If I took 360 divided by 8, I would get the 45 degrees. That is the period. So there we go. That's in radians. And then one last example. That was degrees. If it is in radians, it's the same idea. We're going to take 2 pi divided by the number that the period needs to be. 2 pi divided by 32 pi is 1/16. And so that would be the number that would go into my equation. Y is equal to cosine of 1/16 x, and I'll just have to write that part of it in. 1/16 or x over 16 would be okay also. And now this equation would have a cosine graph that has a period of 32 pi. There we go. I think all I had left was a couple more examples, but I think that's probably enough of the examples. Hopefully you're doing okay with this stuff. As I mentioned before, moving forward, our next lesson is going to be nothing new, just two things at the same time, dealing with amplitude and period at the same time. So if you've got questions, certainly get in touch with me. Otherwise, I will see you again later this week. Bye-bye.